Okay. Okay, so today I'm going to be talking about Fukaya categories, and I'll give a little bit of a background. So actually, I'll go through exactly what I'll talk about today. Specifically, I'll give a background to. Do you have a white hyper? No, that's fine. We'll give a background to Fukaya categories, so kind of where they come from, why we care about them, and this is grounded in string theory and homological and the statement of homological mirror symmetry is directly related to Fukaya categories, which is why we care about them. But the reason for why we came up with this, or why Konstevich came up with the homological mirror symmetry, was due to string theory. So we'll talk about that, and then we'll talk about the construction of Fukaya categories, which just for some Kähler manifold, but that we'll explain that. The Kähler manifold could be relaxed or enlarged to Weinstein manifolds, but we'll get into that. And this construction sort of starts and requires Liouville geometry. So I was told that I write too light on the board, Daniel. Can you see that?
It's visible.
It's visible? I'll write a little harder. I don't know. Yeah. Okay, yeah. And then after we talk about the construction of Fukaya categories, Liouville geometry, and then we're going to talk about the difference between, I'll just write non-wrapped Fukaya categories, so non-wrapped and wrapped Fukaya categories. And actually, at the start of the talk, we're gonna introduce some language which will be later on used for the wrapped sort of stuff. But so just take it for granted when I say certain words, and I'll tell you. Is that what? Oh, thank you. Okay, I just think it might be easier to see on the board. Yeah. Oh, that's beautiful. Thank you. Okay. And I'll tell you exactly when I use that language, and I'll say, don't worry about it. We'll see it later. And then afterwards, I guess we'll kind of talk about, so we'll talk about the construction, and then we'll talk about the category itself, so its objects, so wrapped and non-wrapped, but we'll talk about its objects, its morphisms, sort of the difference categorically between wrapped and non-wrapped, the rigidity of these categories, and then the underlying geometry and sort of what happens there. Okay, so any questions so far? Hopefully none, but so we'll start with the background. Of which I probably won't write a lot in because I don't really know too much about it. And I was hoping that no one from PI would actually be coming here because they'd probably grill me for this one. And then for the people watching, I am learning this as I give this seminar, so go easy on me, I guess. So our background was that in string theory, it just so happens that when you compactify two Calabi-Yau manifolds, when you employ them as the extra dimensions in string theory, you compactify them, you get the same sort of physical theory out of it. And so that kind of posed a problem, because not a problem, but we sort of had this observation where we had these two manifolds, Calabi-Yau manifolds, and they both compactified to the same physical theory. So we kind of thought, what's the relationship between x and y? And this was called mirror symmetry, I believe. This is just called mirror symmetry, I think. And an explanation for mirror symmetry was homological mirror symmetry, HMS, which, roughly speaking, states that the symplectic geometry on X, I'll just say this out loud and I'll write it formally afterwards, the symplectic geometry on X is in some way related to the derived cohomology on Y. And so we write that specifically, and this is where we first see Fukaya X of Y. And so this is the basis of homological mirror symmetry, I think. If anybody has Any other comments on it? Raise your hand. And the mathematical sort of formalisms from that can be stated as follows. If we have some, given some Kähler manifold X, we sort of loosely expect some dual, or some notion of a dual, X check, and then we say then that the Fukaya category of X. And so this is sort of the more mathematical structure. Well, this is, yes.
What is the cohomology theory?
Bad question.
No,
So I only concern myself with the symplectic geometry on this side of the part. I actually have no clue exactly. But however, I did write it down. So if you want, yeah. So it's an equivariant, like the actual language that I should be using is an equivariance of triangulated categories constructed from the derived category of coherent sheaves and the triangulated category constructed from the derived Fukaya category. If that makes any more sense to you.
okay.
Yeah. Yeah. We could definitely talk about it after, make it more like a informal conversation as to more of this side. But I was going to say, before you raise your hand, that this talk is strictly about this side of the equality or connection between the two. So yeah, as I said, Kähler can be relaxed to or enhanced, I guess, to Weinstein manifolds, and specifically Liouville sectors, which is what we're going to start with. Well, not really start with, actually. That's a bad language. We want to get to Liouville sectors. And to do that, we need to first describe what Liouville, it's good if I erase this? You're staring at it, okay. We have to kind of build up to Liouville sectors, which is the fun part. We have to talk about Liouville domains, Liouville manifolds, and only then we can talk about Liouville sectors. And for the most part, this construction is pretty easy. It's not too bad, but we'll start with the domain. So, like any good lecture, we start with a definition. A Liouville domain is a compact, exact, symplectic manifold with boundary. And okay, yeah. So so m to n with some form omega. And okay, so let's go through this piece by piece. So exact for us implies that omega takes the form d lambda for some lambda, and we call this the Liouville 1 form. That's fine. Yep. And then it also has so yeah. So this is only one piece of it. The Liouville domain is a exact symplectic manifold with boundary with an exact form, such that the Liouville vector field Z is outward pointing. So first and foremost, what is the Liouville vector field? Well, we define it because of the fact that this is a symplectic manifold. Our form is non-degenerate. So can I write down here, do you think? Okay. So we can define where Z, I'll write down here, where Z is defined as the inverse of your Liouville 1 form lambda. Or you can equivalently state it as this. This is fine too. But again, the non-degenerate. Oh, this is bad. Well, this is just called the Liouville one form.
Yeah, so it's like the antiderivative of omega. Well, like, what does it mean, omega inverse of lambda?
Well, because it's non-degenerate, we can associate a form to it now. Like, yeah. 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 Yeah, lambda. I don't want to put brackets, but lambda is the, well, I can write it up here. Lambda is called the Liouville one form. Where are we at? Yep, so inverse is always well defined. Oh, so it's outward pointing. So let me just keep this in brackets. So what? So, this. Yeah.
Remember space mechanics, we get like the form, so we have to get a vector field rearranged using the symplectic form instead of the vector. Yeah, makes sense. Maybe I just don't like the notation.
Yeah, I mean, this is another way to characterize the vector field. If you don't like that, this is also valid. Okay, and no, it's fine. And is outwardly pointing. And another way you can think about this is we force it outwardly. Transverse to the boundary of M. So when I sort of show this graphically, I'll be drawing out the vector field, so there shouldn't be a problem. So actually, I'll just start with an example. The sort of canonical example, C star S1, or, yeah. So we have this, and then our Liouville vector field will be pointing sort of up this way, down this way. I mean, I guess, yeah, we'll leave it at that. We could work with coordinates, but it doesn't, yeah, whatever, we'll do that. So like, for example, on here, we have PDQ wedge, and then your Liouville one form is PDQ, and you end up getting that here is P del Q, I think.
So like
No. Sorry, what?
Yeah, so like the way you've drawn it, it looks like the arrows just, they have the same
Oh.
and then they suddenly switch over a different sign when you cross zeros. But like if you write lambda equals some PDQ, P gets smaller.
Yeah, it would. I didn't bother to do that, but
okay.
Yeah, we should be more careful about that. I think for the most part, I won't be caring about that, just the nature of the direction.
I mean, it's still going to be like a smooth form.
Yeah. It's we'll see. I think I don't really care about that because when we have to start talking about the wrapped stuff, you have these points of like, let's just call them discontinuities for now. They're called stops. And then at that point, I don't want to draw like really, really tiny arrows, but I will draw the general direction of the vector field near those stops. But yes, one should be careful about that. And then another example that we see very often in this specific talk is just the disk and with a radially outward vector field. Yeah, it's a radially outward pointing vector field. Okay. So this is fine. So those are just examples of the Liouville domain. And now we'll move on to the sort of the higher or the next step in our construction, which is a Liouville manifold. So our Liouville manifold, M over the boundary of is the cylindricalization of M of the boundary of M. Yeah, actually, this is it. So Liouville domain is to simply, you take your Liouville domain and you sort of glue on infinite cylinders on your boundary. So I'm not going to draw that, but when I do end up drawing some more complicated things, I think it'll be clear why or where we sort of glue on these cylinders. It's actually really important because it's actually really important because in the construction you want to actually cylindricalize away from your discontinuity of your stops, and I'll get to sort of what I mean there. So it's really important as to where this boundary sort of starts and ends, I guess, on your manifold or your domain. So something to note is that if, or I guess given a Liouville domain the boundary is, of course, a dimension less than the manifold is contact. So what I mean by that, what I mean by that is that lambda wedge omega to the, oh, you know what, we'll keep it, this is omega to the n minus 1 is non-degenerate. So this part isn't necessarily too important, but contact geometry does crop up quite a bit in the study of Fukaya categories. Thank you. Not too sure why I did that. I don't even know what that is actually in geometry. Is there even a name for that? Probably not. Yeah, that's what I like, logical, but. Oh, maybe. Yeah.
The Liouville manifold is not necessarily a manifold, right? Because if I have like the two disc and I do that construction, I get a cylinder with two disc in the middle. It's like a torpedo.
Yeah.
Yeah. It's just like the two disc, and then around the boundary you have the entire. Exactly. But that's not a manifold, right? Why not? Because at the point of gluing, you it's like this shape, right? Okay. So like, yeah, you have to.
Yeah, that's why the contact part was really important. There was a large part in the construction, but it sent me down a rabbit hole. But it ends up all working out nicely. But I'd like to avoid as much as possible the contact stuff because I only really started looking into it about like a day or two ago. But it does end up working out nicely and does end up being a manifold. And the other thing that we care about is something called the Legendrian. So a Legendrian, Legendrian is a so lambda is a submanifold. Was an n-1 dimensional submanifold such that. Oh, but this is a. Okay, yeah. It's a. We'll leave it as this for now. But a Legendrian is basically just a submanifold of your boundary, and this is very, very important because it ends up being the case that triple star, a Liouville sector, is determined by the data m and your Legendrian lambda. So this is a, oh, we're getting pretty low here, Liouville domain, and this is your Legendrian. No. I don't know. It could be. I'll tell you what it is. Like, I'll show you diagrammatically how it sort of pans out. If it is, let me know. And it is distinct from Lagrangian too. Is it LE or LA? No, I have it as LA on my notes. Uh-oh. Which one is it? Is it E? It's LE for Legendrian? Okay, thanks. Yes. Yeah. Yeah. How do I do? This might be too low. Yes. Thank you. Thank you. We'll do. So your form vanishes on your Legendrian. Okay. Okay. So the idea behind all this a Liouville sector is obtained by completing M away from our Legendrian, away from lambda. So I guess, yeah, I think it's best if I just, and by completing, I mean the cylindricalization of M away from lambda. And so I think it's really important that we just go straight into a depiction of this. So I don't know when I should define the skeleton, but it's pretty important because it like makes the picture a lot more clear. But you know, here's your M, and your Legendrian is some, you know, these points. I guess it doesn't really matter. You can draw them anywhere. So here it's a this is for n equals 1. So, yep, that's fine. Another classic example for n equals 1 would be the circle. And this image is going to crop up a lot. The circle with 3 sort of points in its Legendrian. And I think the language I'll use later is it's a circle with stops in it, with 3 stops. And so let's take this example. And so this is a Liouville domain and we have our Legendrian, which is the collection of these points. And so let's actually make it into a Liouville sector. And so yes, S1.
Okay, so you're drawing a circle.
Yeah.
Okay.
With like this.
Okay.
Yeah. Good.
Yeah.
Oh no, it's 2. Yeah. This is just a disk.
Yeah, it was also
Yeah.
confused because that one looks like n equals 2 as well.
Yeah.
Or I guess because no, it's 2n.
It's 2n. Yeah.
Ah, okay. So dim is 2.
Yeah.
N is 1. Okay.
Yeah. And then your Legendrian is 1-dimensional in that case.
Oh! Is Legendrian also allowed to be codimension 0?
No. Yeah. Yeah.
But is it allowed to be like a codimension 0 submanifold? Could you have like an interval part of the bounding circle as your Legendrian?
I don't see why not.
You just have to make sure that your one for your contact form vanishes.
I think that's most definitely the case in more complicated examples. These are all like very primitive examples. And I think for the remaining of this lecture, we'll always be working in the n equals 1 case, and our Legendre is just a collection of points. It makes the skeleton actually drawable. I'll explain what the skeleton is in a second, but like in higher dimensions, I don't even know how you'd be able to draw the skeleton of a Fukaya category. I don't even know. But in any case, what ends up happening is, I want to make it the exact same as my notes so I don't mess it up. You kind of have these points, and in a neighborhood, away, completing M away from lambda. I just mean like away from neighborhoods of lambda, and in this case, it's like neighborhoods of these points, and you end up getting the drawing. Don't stay, keep it over there. I just need these. You end up with a nice drawing. So what do I want to do here? I'll make these points red. The stops will make red. Sort of this neighborhood will make blue. And so what you end up getting is, so of course the other thing to remember is that here we have an outward pointing vector field, but sort of what happens around these spots, sorry. No. You want to know? And sort of around these spots, the reason why I didn't want to make it small is because of this, is like our vector field sort of kind of doesn't interact with these stops. They kind of flow away from these stops to avoid any complications. And yeah. And so then our diagram, after you complete it by cylindricalizing, you kind of get this nice picture. Again, with our like vector field, and it sort of goes in that direction, and it's outward pointing. So I think that should be clear from this image. Yeah, and so it's around the white. So on white, you are. And so you're completing away from this blue, and on blue you do nothing. Okay. And so these things, these Liouville sectors that I drew all the way on that end, are the building blocks of your Fukaya categories. And I'll talk about that in a minute. But what's interesting, and I think, William, I mentioned this earlier to you, is that you can glue these sectors together in a very, very nice way. And what I'll do is I'll glue two of these Liouville sectors, the ones that I just drew, with 3 stops on it. So again, I'll explain what stops are, but these sort of points are Legendrian when they're points. I'll just call them stops. So let's make 2. So let's sort of draw our diagram. How do I want to do this? Okay. So here you have the exact same picture, but sort of mirrored. And I want to kind of glue these 2 Liouville sectors together. And, I lied. I said I was going to use red for the stops. But you sort of glue these sectors together, and you glue them on top of your Legendre. You kind of glue 2 stops together. And so this is why I think it is possible to have, like a line as your Legendrian, because I imagine you can glue along like a line as well, and it would probably give you the exact same. But again, for the sake of diagrams being easier, this is the case we're going to go with. And so let's convert this picture. So these are our sectors, sorry, our domains. So we're first going to kind of turn these into their sectors with the stops. I'm very proud of myself for using all these colors. I feel like a topologist, you know. But and so now you can kind of see naturally how these two things glue. And so we'll glue them. Along the stop. And you'll kind of get this picture. How do I do this now? Oh, actually, okay. If you guys don't mind, I'll make it a little bit bigger, I guess. So again, always picture the vector fields in here, the radially outward pointing vector fields. I'm not going to draw them, but since these are domains, they do need their vector fields. And so you're going to glue it by sort of adding in this domain in the middle, which will draw out in full. And thankfully, I don't have to draw the stops. But here, okay, I'm going to state this without sort of definition, but I'm going to draw the skeleton of this domain in orange, and you kind of want the vector field to be tangent to your skeleton along here. And you could think like here we're still, you know, it still kind of all works out because as I said, like as you go here, you're sort of turning out, and on that stop you're like perfectly flat, and so everything kind of just works out nicely. And I've glued it. Oh, thankfully the picture's still there, but that is still a sector itself, and so I've glued it by sort of inserting a sector in the middle. And the nice thing about this is that this is, in effect, if I glue these two, we'll add we'll kind of union. How about that? And then I'll just say this ends up becoming the sort of kind of combining these two together. It becomes a disk with 4 stops. And so in a sense, we can state that the sector disk with 4 stops is equal to the disk with 3 stops glued over a disk with 2 stops. Is the cylindricalization. So yeah, so that's what I wrote here. So on the white spots, you have this sort of infinite cylindricalization, and you kind of don't touch these neighborhoods here in blue. And
white arcs, are we supposed to be imagining like there's infinite extension
yeah,
in some direction?
yeah. And that'll be a lot more clear in a little bit when I talk about the wrapping of the Fukaya category. I don't know how much I want to say about that just yet, but if you're comfortable, just let me kind of just take it for granted. And the picture will be a lot more clear, because what ends up happening is when you don't have these in the category, if you don't have any intersections, you need to sort of infinitely extend it until there are some nice intersections and the category is no longer empty.
The skeleton bit.
I'm going to explain that right now.
Okay.
Yeah.
If you're saying kind of this example, the skeleton is the orange.
Yeah, is the orange line. And I'll explain that right now. The skeleton is right now. And one last thing I want to state, just a little teaser. Oh, okay. A little teaser is that the Fukaya category of this guy can be understood as the Fukaya category of these two guys, of the 2 independent ones glued over the Fukaya category of the middle one. So that makes stuff a lot easier. Sort of the functoriality with inclusion. But that'll be a lot more clear in a second. Yep. No, it's good.
When you see computing, like why are you kind of drawing lines connecting? Like,
Oh, just to really accentuate the fact that we don't touch these guys. That like these neighborhoods remain untouched.
Part of the geometry is just
Nope. Yeah. Sorry. Yeah. This is an actual vector field. This is the vector field. I mean, so you have lambda. Oh, you call it capital lambda or little lambda? Small lambda. Yeah. So lambda is sort of our vector field is determined by. Oh, sorry. Yeah. Our vector field z is determined by lambda. Yeah. The inverse of the Liouville vector form, or the inverse of omega applied to the Liouville vector form. Oh, one form. Okay. Any other questions before I move on? Good. Okay. I'll take a sip. But yeah, like I said, always imagine a sort of vector field drawing. I'll try to add it in, but if I don't, just sort of picture it there. And this is, I really like this. It looks like a face to me, which is why I really like it. But okay, we continue. And I'll talk now a little bit about the skeleton. And the skeleton is kind of nice. Did you have a question? Oh, no. Okay. The skeleton is kind of nice because it's kind of, in a way, up to some form of like topological equivalence. So like you can kind of draw your skeleton however you want. However you want's a little loose, but like, you know what I mean. You can draw it however you want up to it's called Hamiltonian isotopy. We'll get to that in a little bit. So the skeleton has a sort of definition. Well, actually, I can just draw it on these guys. The skeleton has a definition in terms of a Morse function, which is assigned to our manifold. But I won't, again, I asked you guys if that was okay, if I can just skip over that, because I don't fully quite understand it. But basically, if your Morse function is particularly well behaved, the skeleton is really, really nice and it's easy. But it ends up just being the case that your skeleton, we'll draw it on this guy, is sort of the collection of, is sort of the collection of your points in your Legendrian, or kind of just like connects them all. And this is sort of the underlying geometry you can think about. And the other thing is that, you know, sort of this skeleton up to Hamiltonian isotopy is equivalent to this guy. You can draw like big circles around it to make it a little bit more clear. But like you kind of just draw your skeleton however you want, connecting your stops. And yeah.
Is there a particular way we have to connect them? Are
Nope.
there rules for it?
No, not really. The only, yeah.
If I made like a square, that obviously.
Yeah, so there is a little caveat. The only thing you have to make sure is that your vector field behaves nicely. It always has to be pointing off your skeleton for it to encapsulate the same geometry as if I just drew it without the skeleton and I just drew the circle with the 4 stops. And I think that, because you would have inside, because like then you would, exactly. Because I'm thinking this is what you mean, right?
More or less. Yeah.
Okay, yeah. Or. Yeah, you were thinking this, right?
Visually the same though. Like either one of those.
Yeah.
Is different from the other one.
But this cannot be a skeleton, I don't think. Because then you get this picture in the middle, and that's not a, yeah. So there are still some rules, and I think that's, well, not some. I think that's the only rule that you have to make sure when you draw your skeletons. Again, I'm sure if I wrote down the definition in terms of the Morse function, maybe it'll clear that up. And you know what? Just for the people watching, and maybe if this makes any more sense to you, your skeleton, I'll just make a definition here. So your skeleton, do not ask me any questions about this. It's just for those if you actually know it. A skeleton of a Liouville sector. So it's the critical points of the vector field according to some Morse function of the attracting set. Does that make any sense to anybody who does Morse theory? Doesn't make any sense to me yet. So, Jaden, any? Yeah. Anyway, so you can define it in terms of your Morse function. So the other thing, I'll just draw the skeleton on here to make it a little as like another example. You kind of have this guy. Oh, well, I mean we already drew it over there. But here, your skeleton looks a little bit different. Here, it's just kind of like straight lines. I don't want to do this. So this one's actually interesting. I don't know how it works. I just realized, how would the skeleton look like if you only had a point on the front side and a point on the back side? Well, I guess in that matter, in that regard, you can kind of unfold the cylinder by identifying the two sides, and then maybe your skeleton will just look like this. Yeah, I think it curls around, and there's no problem with anything. Yeah. But I like uncurling my cylinder, so I like that description. Okay. And I said it's like up to Hamiltonian isotopy that you get these different skeletons. Okay. Okay. What's next? Any questions about the skeleton? I'll be drawing the skeleton a lot more clear now. Like on every single one, I'm going to be drawing my skeleton.
I know you didn't want any questions,
Okay. But no promises that I can answer. I'll try my best.
Yeah, try not to be like too. Like, I just want to know: is it something that you would derive from your symplectic form or the Liouville form, or is it an additional thing that you put on top?
So it's an additional thing. Like if I recall, it has to be that your vector field. It's like if your vector field is well behaved, like gradient-like, I think it was the description of it. Then this is the definition you would use for a Morse function on your manifold, but
Because that vector field would just be the gradient.
Yeah. Yeah. Good. Okay. Yeah. Yeah, and it kind of just like a sort of more fundamental object that you can work with. Because then, we don't really got to draw the circle anymore. You can just draw your skeleton, and you know exactly what it is. Okay. Okay. Oh, yeah, okay. Well, so here's the only defining factor of your skeleton is that your Liouville vector field has to look like the cotangent to this skeleton. So I guess that's what I said earlier. It's got to be outward pointing to the skeleton. Okay. All right, let's go through. I want to keep that picture up because it's a really nice picture of the gluing. But let's go through another gluing example. And this one I very much enjoy because it's a pair of pants. And who doesn't like pants? So it turns out that we can draw our pants, or we can glue together two very specific cylinders with two very specific stops. So let me draw the cylinder out first. Oh, that might be too much. Okay, I'll erase that. It's okay. And then our stops that we want are sort of just defined on one end of the boundary. Blue. Defined on one end of the boundary. Sorry, Will, I'm going to put these here. Oh yeah, you get to look ahead. So you kind of have this stop here, and then you have this stop here, or this is your Legrandrian on each one, and yeah, no other stops, and you sort of glue together. How do I do this? You glue these two together by gluing a cylinder with two stops, or Disk with 2 stops. Thank you. Disk with 2 stops. And so you know this has a skeleton that looks like this. It's sort of with a vector field. I know I said I wasn't going to draw it, but I'll just draw it on this one. Sort of a vector field pointing out. And I kind of already gave away the answer, but if you stare at it long enough, this ends up being a pair of pants. So you do is you kind of glue them together, and then you complete. I'm trying to draw these pretty big so that the people online can see. Hopefully the pictures are big enough, Daniel. But this, once you glue everything together and then complete, then you would get your so hold on now. I need to check where my stops end up. Oh, I didn't. But here's your sort of first cylinder, your second one, and then your vector field, sort of outwards, outwards. And so we say that this is sort of equal to the union over a disk with 2 stops, another cylinder, short and red. So this, in Liouville geometry, your symplectic pants is this. This is how we view a pair of symplectic pants. And again, we always kind of want to view it at this level because as you'll see, the Fukaya category of your pants is just the Fukaya category of this one and this one over the Fukaya category, glued over the Fukaya category of that one. So it makes things a lot nicer. Okay, let's see. Okay, any questions? I am going to move on to non-wrapped Fukaya categories now and wrapped Fukaya categories. So this will be kind of we're done the construction. We're done this step of the construction. That non-degenerate. Oh, that's a good question. I don't know.
Because it's just d of lambda.
But if lambda is 0 on your Legendrian.
Because it's dual to the vector field. But it could be 0. What do you mean?
You mean omega is 0?
Like lambda could be 0 there, but then d lambda is not actually 0 there? Right.
Is that real? Is it real and true? I guess, yeah. Yeah, because then we don't have to worry about non-degeneracy anymore. Yeah, these are closed. And again, like I don't really want to draw it out, but there's like infinite cylinders along all these. It's a little bit iffy. I tend to not visualize the cylinders at all, and I just visualize the underlying geometry with Legendrians. Yeah, because then, these skeletons, you bypass that problem completely. And so, wait, yeah, it's nice. Yeah.
I'm confused about the first equal sign.
I wouldn't really take the equal sign literally. It's just like, after gluing these together and then topologically or Hamiltonian up to Hamiltonian isotopy, it ends up being a pair of symplectic pants. I should have put quotation marks here too.
Right.
Equal sign is not actually equals.
Everything we consider is up to Hamiltonian.
Yep. Yeah. And that's a very, Like the skeleton? Yeah. That's a good question. It definitely could. Like I can see it doing that, but I think it is just more convenience than anything. Like the other thing is that like we spoke about how different skeletons, you can draw different skeletons. So classification just might be a little bit iffy because like if I'm able to classify them, but then I just add like a little line here, you know, I mean, why are we even classifying them if I can always just change it up to isotopy, Hamiltonian isotopy? Yeah, I mean that too. It also just makes the categorical picture much nicer. Wow, yeah, okay. So big spoiler, but yes, that is kind of what happens in the wrapped category. You end up like, well, this okay. This will be a sneak peek because we're going to talk about it in a second. But if you have some sort of Lagrangian submanifold on your Liouville manifold, you can sort of wrap it, which amounts to sort of literally just kind of flowing it along the line, and you can bring your Lagrangian up to those stops. It's not that you can identify the stops with each other, but you can identify Lagrangian up to a stop. So we'll get to that. But you cannot move the stops. You can't move them. You can't combine. Okay. Oh. Maybe you can. Because I guess in a sense when you glue these together, you are identifying these two stops together. So when you glue things, I think the skeleton makes it clear that you identify these two together. But other than that, I don't think that's the case. Will, your face of confusion worries me. Like which? Because I'll let you know in case. Yeah, if by the end I haven't answered them yet, do let me know, and we'll get to them. Okay. So. Okay, so now I want to talk about the non-wrapped and wrapped Fukaya categories. So, yeah, I'll just erase all this before I get to talking. I guess I could. So, I mentioned this before the mic got turned on and before some of you guys were here. So maybe I'll just give like a little sneak peek again. But the reason why we need these wrapped and non-wrapped, or we need wrapped Fukaya categories, is because in the non-wrapped case, it comes up from a compact. Everything is compact, everything's nice, there's nothing really wrong. Our Lagrangian submanifolds are well behaved inside, but in the non-packed case, and our Lagrangians kind of transverse nicely, or they intersect transversely, I should say. And so your fluorocohomology is all nice and well defined. But in some cases, that's not, in the non-compact case, they might not even intersect at all, or they might intersect at infinitely many points. And so it kind of gets a little messy. And then the structure that you get when you look at the non-wrapped Fukaya category might be trivial. So like there's nothing. Like it might not even pick up intersections. And in which case that's bad, because obviously there are intersections. And so then you introduce the language of a wrapped Fukaya category, which fixes that problem, allows us to see the intersections in the fluorocohomology, or the intersections from the fluorocohomology. And not only that, the wrapped Fukaya category, I believe, is just structurally, I'm going to say nicer, but I think that's just personal bias. It could be, I'll let you guys decide that. So, okay, we'll start with the definition. A non-wrapped Fukaya category M, and then our Legendrian. How do I write this? Okay, I'll leave it as this for now. Wrapped Fukaya categories will do W of this data, but I'll just say that a non-wrapped Fukaya category is a category over this data. Has objects, so it has objects. I heard a sigh. Is there problems with that? I don't know. But so the objects are exact Lagrangian submanifolds disjoint from our Legendrian such that our Lagrangian intersects transversely to the boundary. So it's transverse, or yeah, it's transverse to the boundary. And so what I mean by that is, let's have a picture here. I won't draw the full picture, but if you had our lovely example of the cylinder and you had a sort of Lagrangian submanifold doing God knows what, as soon as it hits the boundary, it's sort of well behaved in that cylindricalization. Kind of blows off nicely to infinity in a straight line, I guess, in this example. But all I meant to say is that it's cylindrical at infinity, so it kind of just passes just straight line up the cylinder, cylindricalization. But inside, it can do whatever it wants. It doesn't matter. Maybe I will draw this picture. Well, better hope it does. I mean, that's the whole point. I'll get to the morphisms of this category, but the morphisms are the Floer cohomology of our Lagrangian submanifolds, which is loosely defined as the intersections, basically. So I kind of want them to intersect. And so our objects are this, and our morphisms. Do you want to say that? Okay. There's like extra data that you get in the objects, like grading and orientation. No, I'll skip it. It's not that important. It'll just confuse people. It's not important. That data is not important. It might be important at some point, but for our sake for today, it's not important. And our morphisms between two Lagrangian submanifolds are the Homs between L1 and L2 with, and this is what I was saying, Daniel, you want your Lagrangians to be transverse. What else? Is the Floer cohomology so in other words, Hom L1, L2 is the Floer homology of L1 and L2. Lagrangian submanifolds, yeah. That's the definition. Yeah, sorry. Boop. Did you do that? Floer homology, core homology doesn't actually matter. Because later on when we talk about limits and like when you apply wrappings, you take that the Floer cohomology or homology is either the limits or the colimits. It doesn't actually matter over all the wrappings. So it's up to whatever you want. Okay, so I was not ready for that question. See it. So, okay, so it's a. Would you be content in saying that it's just the intersections? It's like an enumerative thing. It counts the intersections between your. There is a category. There is a definition that'll come later, in terms of the limits of wrappings. Yeah, transverse intersections of Lagrangian submanifolds.
So what is a Lagrangian submanifold again?
N-dimensional. So like M is 2 n-dimensional. L is n-dimensional, which vanishes on the boundary. No, that doesn't make any sense. Hold on. Omega vanishes on the boundary. Yeah.
What does it mean to be exact?
So transverse. So what the? Oh, wrong way. For L to be exact, then our form restricted to L is df for some f from L to R. Is exact. I probably shouldn't use lambda there. I don't think. Yeah. Is it lambda or is it omega?
Is it the lambda that we got from our omega? Like it's an derivative of the omega?
Has to be.
I think it has to be, yeah, little lambda. This is true. This is true.
So
Yeah,
it has to be
it has to be lambda.
that.
Yeah.
So L1 intersect L2 is just the number of points. So they're to be transversely intersecting half-dimensional submanifolds, and their transverse intersection is just the discrete set.
Yeah, it's a collection of points. I mean, like there is an exact definition for the differential. Oh boy. Okay. So like the differential, it pretty much just like counts. I'm gonna write this down. So this is a very pictorial definition. So it's kind of the amount of intersections between L1 and L2. Counts the amount of intersections. There's probably a better drawing for this, but this is your differential, and then it encodes the amount of intersections between two Lagrangian submanifolds. Don't take that seriously. Don't take it seriously.
And that's the coefficient of Q. The number of intersections, does that become the coefficient of Q?
Yeah.
The only thing is, I just don't see how that's like a homology.
Yeah. Okay. So this is a. Okay. So this is a chain complex with a vector space basis, I guess. Given by L1 intersect L2. And this is inherently finite since L1 is transverse to L2. And yeah, and then I have if P is in L1, L2, then dP